In this lesson, we'll continue our discussion on big idea number 2. So how does the structure of an organic compound determine its physical and chemical properties? And start our discussion on learning target number 2. Can you compare the structural differences of each of the organic families and predict their physical properties based on their structures by looking at the functional group the molecule has? Functional groups are special structures added to alkanes that can change their intermolecular forces. This changes the physical and chemical properties, creating a new organic family. The first thing that can be added to an alkane is a double bond between two carbons. Adding a double bond does not change the polarity of the organic compound. This means that the organic compound can still only use London dispersion forces. However, whenever you put a double bond on a compound, you have to remove two hydrogen atoms. Because of this, your molecule is smaller, which makes the London dispersion forces weaker than if there was a single bond there. This means for every double bond included on the compound, it lowers the melting point. And it also makes the compound softer. When we talk about solubility, remember we have to describe the intermolecular force that water can make with the chemical we're trying to dissolve. Because adding a double bond onto a compound doesn't change its polarity, it's still nonpolar. It doesn't change the solubility of a compound. Another functional group you can add onto an organic is a C-to-C triple bond. This also does not affect the polarity of the compound. So it can only use London dispersion forces to attract another molecule. Now you might think, because we have to remove two more H's to change a double bond into a triple bond, it would have weaker London dispersion forces. However, whenever we have a triple bond, we introduce a linear Vesper shape around our carbons. These are easier to pack into a crystal, which creates stronger London dispersions than a double bond or even a single bond. This increases the melting point and makes the compound harder. In terms of solubility, because adding a triple bond does not change the polarity of the compound, it has no effect on the solubility. Another functional group is known as a hydroxyl group. It's where you have a carbon that is single bonded to an oxygen, which is also attached to a hydrogen. It could be short formed by doing this. Because I have polar CO bonds and polar CH bonds, I will have slight charges on my organic compound. This makes my compound polar. Because I have an H directly attached to an O, if I have two organic compounds with hydroxyl groups on them, they can make a hydrogen bond, which will increase the melting point and increase the hardness of the solid. If I try to dissolve a compound with a hydroxyl group in water, because it has an O and an H in it, it can make a hydrogen bond with water. This increases the solubility of the compound. The next functional group is known as an alkoxy functional group. It occurs when you have an oxygen that is single bonded to two carbons. Because you have polar CO bonds, you'll have slight charges, which makes your compound polar. Because there is no H directly attached to the O, you cannot hydrogen bond, but you can make one dipole-dipole attraction with your slight charges. This increases the melting point and increases the hardness of your compound. When I try to dissolve an alkoxy functional group in water, I can actually accept a hydrogen bond. The definition of hydrogen bond is an H directly attached to an O, N or F, which is supplied by the water, and a lone pair of electrons on an O, N or F on the neighboring molecule. That is supplied by the alkoxy group. We distinguish making and accepting hydrogen bonds. If your organic compound has an H directly attached, it can make a hydrogen bond. If it does not, then it can only accept a hydrogen bond. This will increase the solubility of the compound. Now, one important thing to note is that accepting hydrogen bonds only affects the solubility of the compound and not the hardness and the melting point. Remember, when we take two alkoxy groups and try and stick them together, we can only use a dipole-dipole attraction. Neither of the molecules has an H directly attached. The difference between accepting and making hydrogen bonds is summarized in a box at the bottom of the note. The next functional group that you can add is known as an amine. It's when you add a nitrogen onto your organic compound. Now there's three different ways that you can do this because nitrogen can bond up to three different atoms. A primary amine is where you have one carbon attached to your nitrogen. A secondary amine is when your nitrogen is attached to two carbons. And a tertiary amine is when your nitrogen is attached to three carbons. Now, each of these nitrogens also has a lone pair of electrons on it, which gives it a trigonal pyramidal shape around the nitrogen. Because I have polar CN bonds and polar NH bonds, this makes my compound polar. Where the carbons would be slightly positive, my nitrogen would be slightly negative, and my hydrogens would be slightly positive on each variation of the amine. Now, each classification of amine can make a different intermolecular force. If you have a look at the primary amine, I have two H's directly attached to a nitrogen. Therefore, it can make two hydrogen bonds. If I compare that to the tertiary amine, it does not have any hydrogens attached to the nitrogen. Therefore, it can only form dipole-dipole attractions. All of these intermolecular forces increase the melting point and increase the hardness. Again, in terms of solubility, there is a range for amine functional groups, depending on which classification you have. If you have a primary amine, you can make two hydrogen bonds with water. If you have a secondary amine, you can make one hydrogen bond with water. And if you have a tertiary amine, it can accept one hydrogen bond. From water. This is because there are no hydrogens attached to the molecule. The water will supply the H directly attached to the O, and the nitrogen supplies the lone pair to complete the hydrogen bond. All of these intermolecular forces increase the solubility of the compound.